Here's a nice mathematical puzzle which I came across a few years ago in the churchyard of St Mary's Priory Church in Monmouth in the UK. So there's a headstone marking a grave in the churchyard there, which is inscribed with a grid of letters, an acrostic, which I've drawn out here. And if you look closely, you'll see that there's a message, an epitaph, inscribed in these letters here. So the idea is that you start from the central H here and you read zigzag fashion out towards any of the four corners, and for example, if we read across here and then up this way, then we can read the message, the epitaph. Here lies John Renie. And similarly, we can read it in any other direction or in a zigzag fashion. For example, down here we can read the same message. And the story goes that John Renie designed and inscribed the gravestone himself in order to confuse the devil, because in order to claim his soul, the devil would have to be able to read the name contained in the headstone, and this acrostic would confuse him. So the question is, how many different ways are there to read that epitaph, that message? Well, if you Google the gravestone of John Renie in St Mary's Church in Monmouth, you'll find several websites that describe it, and they all tell the same story, but they give different values for the number of ways. So, for example, one website which credits the British Society for the History of Mathematics with this value, they give a value of 32,032. And another website gives a value of 46,000, which could be an approximation. And a third website gives a value of 45,760. So I wanted to know which was the correct value, so I sat down with a pencil and paper, and I thought that, well, my first thought was that I could divide the problem into four by just considering a single quarter of the grid, and then I could multiply the answer that I got by 4 to give the whole answer. So let's take the top quarter here. So if we start from the H, then there are always going to be 16 moves to do, and it's always going to be 10 moves across this way. No, it isn't. 9 moves across this way and 7 moves up. So we're always going to make 16 moves, and it's always going to be 9 moves across and 7 moves up. So let's count them out just to check. 1, 2, 3, 4, 5, 6, 7, 8, 9 moves across. 1, 2, 3, 4, 5, 6, 7 moves up. And it'll be the same whatever zigzag path we take. So my thought was that I could use a kind of an induction to solve this by saying, well, for the first move, there are only 2 choices. We either go across here or we go up here, and then we have a smaller problem to solve. So, for example, if we go up here, then the problem becomes one for a smaller grid that I've outlined here that measures 10 by 7. Or if we go across this way to start, then we've got a grid measuring 9 by 8. So we can add up the 2 results that we get for those. So that was my thought, was that I could reduce it to smaller and smaller grids and then just add up all the answers. But well, I did get the solution, and it was the right answer, but it was a bit messy because of the way that those smaller grids overlap. So it certainly wasn't the right way to solve the problem. So I'll show you a more elegant analysis now. So let me just move the board up so that we can see what we're doing. I've got a space to work. So as I said, there are always going to be 16 moves, and it'll always be 9 moves across and 7 moves up. And that's really all we need to know, because the problem then is equivalent to saying, how do we choose which of our moves are across and which of our moves are up. So that problem is well known to mathematicians. It's a problem in permutations and combinations, and we're saying, how do you choose 9 things from 16? Or equivalently, how do you choose 7 things from 16? And mathematicians have a notation for that, which is written like this, NCR. That's how do you choose R things from N. It's also sometimes written, well, it's more popular now to write it this way. And there's a formula for it, and the formula is N factorial divided by R factorial times N minus R factorial. So in our case, that would be 16 factorial divided by 9 factorial multiplied by 16 minus 9, which is 7 factorial. Okay, so we can write that out longhand and figure it out. So we get 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 down to there. And then on the denominator we've got the same 9 times 8 that are going to cancel with this one. And then we've got 7 times 6 times 5 times 4 times 3 times 2. I won't bother saying times 1. Okay, so let's cancel some more. So we can cancel the 4 and the 3 here with that 12. And we can cancel the 2 and the 5 with that 10. So then we can cancel 3 from here, and change that to a 5, and we'll cancel that 2 and change that to an 8. So, and we'll take that one there, cancel it with there, and get 2. So I get 8 times 5 times 2, which is 80, times 13 times 11. So that's 880 times 13. So that's 0, 3 8s are 24, 3 8s are 24, and 2 is 26. And then we've got 880 here. So there's 0, 4, 4, 11. So that's my answer, 11,440. And if we multiply that by 4, we get 0, 16, carry 1, 16, carry 1, the 1 is 17, 5 and 4, 45,760, which was actually one of the values that was given on the website. And to be fair, the other website that said 46,000 was probably just approximating to that answer. So I think the thing that's difficult to see with this problem is that business about choosing 9 and 7 things from 16. So I'm just going to make it a little bit more clear. So for example, if we imagine that we write the letters out, H, E, R, E, L, I, E, S, J, O, H, N, R, E, N, I, E. Now, we're starting from the H, so it's kind of, we can say that the H is fixed, and the choices that we make are for the subsequent moves or the subsequent letters. So I'm going to say, let's just push that H over to one side and choose from the other 16 letters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're going to just choose 7 things from 16. So I'm going to choose 7 of these letters, and I'm going to mark the ones that I choose with a little arrow. So I'll have that one, and that one, and that one, and I'll have that one as well. So that's 4, 5, and I'll have that one and that one. 7. 1, 2, 3, 4, 5, 6, 7. Okay, and effectively I've chosen the other 9 because I could just as easily have said, can you choose 9 of those 16 and mark them with a little arrow? And so here's the 9 that I might have chosen. 1, 2, 3, 4, 5, 6, 7, 8, 9. So by choosing 7 and marking them with a little down arrow, it's the same thing as choosing 9. And actually, I'm going to mark the ones that I've chosen, the 9 that I've chosen with a little arrow here. Can you see what I'm doing now? So I'm showing you that by making those choices, we can define a unique path that takes us from the central H. In this case, we're looking at the bottom corner of the grid, starting from the centre of H to the bottom corner here. So what I'm saying is we're going to go from the H, we're going to go across to the E, down to the R, then we're going to go across to this E here, then across again to the L, then down 3, so we're going to go down to the I, down to the E, down to the S, then we're going to go across 2, so that's across here to the J and the O, then we're going to go down 1 to the H, then we're going to go across here to the N and across again to the R, then we're going to go down to the E, down to the N, and then across the last 2. So by making that choice, we've defined a path, and similarly by marking out any zigzag path, that would define a choice of 7 downs and 9 across moves. So you can see that that's why the answer to the problem comes from the formula for choosing 7 things from 16 or 9 things from 16.